All right. Well, happy Friday, everybody. And I think I want to show a little demonstration of basically the neural network in kind of an image recognition example. This is a very simple and rudimentary example, but yeah, it works, kind of, mostly. So anyway, let's try this out. So we are going to work with the MNIST handwritten digits data set. This is a very popular data set for image recognition. And so I have this link. It says how to download and set up the MNIST data on your computer. So what you'll need to do is like, if you want to do this on your own machine, which you can, you'll have to download the R scripts, put them into a folder, and then within that folder, create a subfolder called MNIST. And this is where you're going to put in your data, okay? So let me go ahead. I'm going to open up these two R scripts, and I'm going to download them first, okay? So download MNIST neural network. I'm going to click download there. And here, let me open up my downloads folder. So I'm going to create a new folder within downloads. I'm going to call this neural network demo. And then I'm going to move that MNIST R script into the neural networks demo folder. And then same thing here. I'm going to download this R script for loading the data. And let's see, we're going to move that into the neural network demo. Here, let me open up this folder. So I've got my two scripts inside this folder within downloads. And then within this folder, I'm going to create another folder. And I'm going to title this MNIST. Okay, and this is where I'm going to put in the data. All right, so does that kind of make sense? So just, you have a folder, you have your R scripts in your folder. Inside that folder also, there's another folder called MNIST. I'm going to download these data files into there. So these I'm going to just click and download from here. And I'll click all four of them. Let me just have all four of these. So these are all, I don't know, something ubyte.gz. And I'm going to drag them into neural network demo. And then I'm going to just drag them one more time into my MNIST folder, okay? And so now I have my four data files. Now, we have to un-GZ them, which if you're on a Mac, you can do this from the terminal, but I don't think on on Windows I can run this. I'm going to just try it, but I'm pretty sure it's not going to work. G-unzip. I think I'm going to get an error. Yeah, G-unzip is not a recognized term. But on Mac, you should be able to do it. So so you have your MNIST folder. So on Windows, I use a program called 7-Zip. 7-Zip is free to download, and I'm going to just unzip all of these. I have to go to show more options under 7-Zip. I'm going to just do extract here. I'm going to do that for all four of these .gz files. 7-Zip extract right here. Where is it? Show more options. 7-Zip extract here. And some will come out to be a little bit bigger. Extract here. Okay, so yeah, the big one is around, after unzipping, is around 45,000 kilobits, about 45 megs. I mean, not that big, but yeah, there's lots of data files. And you can see the dates on these things are from, what, 1996? And this is, yeah, these are old. The data is back from the 90s. And the application, if you go online and you just type in MNIST data, you'll see all kinds of stuff, and you'll find like on Kaggle they have this, but I don't recommend using the Kaggle thing just because. Okay, actually, well here it's the UByte file, so that's fine. But sometimes you'll see them like formatted as CSV files and things like that, and I don't recommend it. Okay, so this came from in the late 1980s and early 1990s. The Postal Service had employed a lot of humans to sort mail, okay? And basically they would read the address. They had kind of just implemented the zip code, and using the zip code, they would sort the mail into different facilities, and it required a human to, anytime there was handwritten letters and stuff, a human would read it and then say, okay, well, this is zip code, 90210, so that's going to Beverly Hills, right? And this one is, I don't know, something else, and it's going somewhere else. And this required a lot of resources. And so they said, well, can we get a computer to be able to read these handwritten digits? And so they spent a lot of time scanning, okay, digitizing a whole bunch of these images. Let me see if I can get a better picture, okay? And so one reason why the MNIST dataset is so popular is that all of the images are very kind of clean and like perfectly formatted, in that you have this, somebody spent a lot of time basically scanning all of these things. They labeled, and then they cropped them down to these, little squares, where basically each square has a digit drawn in it, okay? And so you have these different things, and sometimes you see it's black on white or white on black, but it doesn't matter. Basically, you have this 28 by 28 pixel image, and within that image, each pixel is represented with a number between 0 and 255, okay? So basically, 2 to the 8th power, 0 to 255, and basically, in this case, 255 would indicate the pixel is white, and 0 would indicate it's black, or in this case, just kind of the flip side, 255 would indicate a black pixel, and 0 would indicate a white pixel. Whether it's, basically ink, and then, a number like 100 would be, some shade of gray between, the two extremes there. Okay, so this is kind of a very clean data set, but we have the problem of trying to take this thing of pixels and we want to be able to say, all right, this thing is an 8, this thing is an 8, and this is an 8, this is a 2, that's a 1, that's a 6, that's a 9, that's a 5, so on and so forth, okay? And it is kind of incredible that as humans, our brains are able to do this, okay? And anyway, the question is, can we train a computer to do something like this? All right. So anyway, I have my data downloaded, and I have them all unzipped, and I have my 2 scripts here. Okay. So I'm going to go ahead and open these in R, or RStudio. So I'm going to open up the load data and the neural network. Okay. So the load data is a script that I got from the internet, and this will basically read in binary files, which is what we have. Okay. Here I have. If you decide not to create a subfolder called MNIST, then you might have to change the address here. But this here I've got, basically it says within the MNIST file, find this UByte file. Okay, so I'm gonna load up that function and then this function, and basically I'm gonna load in the data. So I'm gonna run load MNIST, and that is going to bring in the data, and I've got train and test, okay? basically, I have 60,000 training images and 10,000 test images. Okay, my training matrix has 60,000 rows. One row is one image, and each image is 28 by 28 pixels. Okay, but what they did was basically all of the pixels, they took them from 28 by 28, and then they just kind of turned it into just one long row of 784. Okay, so kind of like how R stores a matrix, both as kind of a two-dimensional structure, but it's also just kind of a single vector with dimensions applied. Basically, they just said, all right, if we just take the 28 by 28 pixels and we don't represent them in a square, but just turn them into just one long thing of 784 values, that's what we have. And so, I could look at one of the rows here and say train $x, and we'll just look at like the first row, okay? And you can see it's just 784 values. Some of them are zeros, and some of them are have numbers. And kind of like an interesting thing is if I set the width of my thing, let me just see if I can do this. If I can get the width just right, so I get 27. If I can get just a little bit wider, like there we go. Okay, so now in this thing I have 28 values. So this is all 784 values, but I have it printed so that 28 values kind of fit across the row. And you can kind of see the structure of this, because when there's a 253 here, like it just takes up more space. And so it like appears darker, right? And so we can kind of make out this, like the image here, and what would we say this digit is? It looks like a 5, right? Okay, and that's just kind of a, like, in a weird sense that like the zeros take up less space and the 253 takes up more space, and so it almost looks like you can see the pixels themselves. Okay, but anyway, that's not the intention. It's still just a kind of 784 values in a row. We have a function called showDigit where I can kind of basically take that vector of 784 values, and it will create a plot. Whoops. Figure margin's too large. Let's go ahead and try this again. All right, and so here it plots the image here. Okay. And I could say, all right, let's look, and we can also look at the label. So the labels are do I not have, what is it? The Y. Oh, no, I don't need showDigit. Okay, so the label is just under train $y, and yeah, the label for that is a number 5, as we might expect. Okay, and we could just kind of inspect a few of the other digits. So the second digit looks like that, and the label is a 0, as we would expect. Here's our third digit, and the label there is a 4. And here's just kind of like the fourth digit and the fifth digit, and so on and so forth. And so all of these images are insider data. Okay. And so what we want to do now is we want to train a neural network so that we can put in as our input this vector of 784 values, and as an output it will give us a label and say this is the digit 9 or this is the digit 5 or something like that. So we're gonna set up our neural network like that. I forgot about view quiz stuff. I gotta log in over here. Okay, so yeah, this is just an example. This is kind of our first value. All right, so one thing we will need to do is our label here says, hey, this is the digit 5. But what we need to do is we are going to have one node for every possible label. Okay, so because the digit label is not, this feels weird, but it's not numeric. Okay, when we say this digit is the number 5, right, that is not a numeric value. Okay, when we say, you know, this digit is 9, it is not a numeric value. And that feels weird because it's like, it's a 5 and it's a 9. But basically we are labeling as a category, all right? Kind of like if it were the letter A or the letter B, like labeling a squiggle as number 5 is no different than labeling a squiggle as the letter B, okay? Or labeling it as the letter K or something like that. And if you think about it that way, then yeah, it kind of makes more sense as a categorical thing. Another reason why it is not numeric is if I were to label this incorrectly, okay, so the correct answer is 9, okay, and if I were to label it incorrectly, and if I were to incorrectly label it as the number 8, and someone else were to incorrectly label it as the number 1, as a numeric response, we would say that 8 is less wrong than the number 1. Okay, if it was numeric, right? Because if you're thinking about like regression and like sum of squared errors, we would say the difference between 9 and 8 is only 1, and the difference between 9 and 1 is, you know, there's 8 points, and so you know, one has bigger error than the other, and we'd say this one does a better fit. But if the digit is 9 and somebody labels it an 8 and somebody else labels it a 1, they're both equally wrong. Okay, they are both equally wrong in that they both got it wrong. So as far as getting the label correct, it's either you're correct or you're wrong. There's no different degrees, like this one is less wrong and this one is more wrong. They're just wrong. And using a numeric value would treat the errors different. Okay, I got to log in over here. Give me a second. All right, okay. First view quiz answer is the letter C. C as in cat. C as in cat. Okay, so in order for us to treat this as a categorical thing, in our output layer, rather than just having one node, and the one node being like the number that we're going to get, we need 10 different nodes, okay? We're going to have a node for each possible label. So we'll have a node for label 0, and a node for label 1, and a node for label 2, all the way down to node label 9, okay? And then therefore, when if the actual label is digit 9, then the correct output should be 0s for all of the nodes for labels 0 through 8, and then a 1 for the node for label 9, okay? And then if we have, say, digit 5, then basically our output should be 0, 0, 0, 0, 0, 0, 0, 1, okay, and then 0, 0, 0 for the other nodes, right? So we need a 1 for the node for label 5, and then zeros for everywhere else. So basically, I'm going to have this function, and we're going to apply it to our data, okay? And so, for example, this is after I've applied this function, which is basically, it's going to start off with zeros for all 10 nodes, and then it will just replace it depending on what the label is. It's going to replace that particular node with a 1. Okay, and I have j plus 1 because the first node is 0, and the 10th node is for the number 9. And so for our first image, the label is a 5, so we're going to have 0, 0, 0, 0, 0, and then a 1. This is the node corresponding to label 5, and zeros everywhere else. Our second image is a 0, and we're going to put a 1 for our first node, which corresponds to label 0, and then zeros for everywhere else. Okay, so this is basically our target data. Okay, we want the output of our neural network to basically look like this row, and we want the output of this, for that, and then this image to look like this. This is the target. Okay. All right. So yeah, we'll take a look. Okay. we are going to put in our functions. And so again, basically I just copied and pasted the code that I showed you on Monday. On Monday, we had like a very basic neural network with 2 nodes in the input layer and 1 node in the output layer. I'm doing, basically I copied and pasted that, except the thing I'm changing now is that my input layer has 784 nodes to represent the 28 by 28 pixel image, right? So we're taking our 28 by 28 pixel image. So now my input layer has 784 nodes. My output layer is going to have 10 nodes, 1 node for each possible label. And then I just arbitrarily chose to have 30 nodes in the hidden layer. We could have more, we could have fewer. It doesn't really matter. I just arbitrarily chose 30 just because it seemed like a reasonable number. And I think that was just like the first number that I put in there. And then I ran it and it worked well enough. So I said, all right, we'll just stick with it and we're not going to try to break it. Okay. Okay. So now I have these 2 weight matrices and they're, this first one's pretty big because the first weight matrix, I've got 784 nodes going to 30 nodes. Every node is connected to every node in this layer is connected to every node in the next layer. So we're going to have 784 times 30. What is that? 784 times 30, that is 23,520 weights. Okay, so that's a lot of weights to train. And then going from our second weight matrix, going from our hidden layer to our output layer, we're going to have 300 weights, 30 by 10. Okay, and so anyway, my initial values, I'm going to just put in just initial weights in my to do gradient descent. We're going to just put in initial weights and then we'll go. So I'm going to just fill it in with random values in order to kind of just get some. I want both positive and negative values here. I'm going to just say random uniform. Pick a random uniform number, which is going to be between 0 and 1, and then I'm going to just subtract off 0.5. And so then I'll get a random value between negative 0.5 and positive 0.5, okay? And I'm going to just arrange these into a W1 and W2 matrix. And so you can see W1 is 784 by 30. W2 is going to be 30 by 10, okay? When I train the network, okay, the way we did it in Monday was we said, okay, we had our input layer, we calculated our gradient, and we went downhill. Now, we could do that, except because I've got 60,000 images in my training data, when I do forward feed, okay, and I say, okay, we're going to do our input matrix X is 60,000 by 784, and then we go to the next layer and do all of these calculations. There's just a ton of numbers, and it's going to kind of bog down my computer. Now, if you have like a very kind of and I don't have my computer set up to take advantage of like GPUs or anything like that. You could do that. You could set up like CUDA on if you have like NVIDIA graphics cards, you can set up CUDA and things like that. But anyway, 60,000 is kind of a big matrix. So we are going to do something called batch gradient descent. Okay, and basically you are when you calculate the gradient, you're taking basically the difference between your actual values and your predicted values. And if you do the full data set, you'll have 60,000 actual values and 60,000 predicted values. And you say like, okay, what's the difference between these things? That's going to determine your gradient. When you do batch gradient descent, you basically take a subset. And I'm going to do small batches. I'm going to just basically take 10 images, right? And I'm going to get 10 predicted y hats, and then I'll compare them to the 10 actual values. And then I'll just use that to calculate an approximate gradient, okay? So it's kind of, you can think of, like if you wanted to no public opinion, you could run an election, okay, and have everybody vote. And it's a very kind of costly and time-consuming thing because you got to send out ballots and you got to have polling stations, but then you get like the entire country's vote or whoever showed up to vote that day, and you can say, okay, well, this is who the country wants to elect at this moment in time, okay? But then, like, as the months go by, public opinion changes and things like that, and to kind of keep up with that, we don't run an election every single time. But we run like a little poll and we say like, okay, we surveyed 800 people and this is kind of what they said. And that's supposed to be like sort of representative of what, the overall general, opinion is, okay? And this is kind of like that, except we're not going to do all 60,000 to figure out what the gradient is. We're going to just take like a random sample, in this case, like a really small one, 10, and that will give us like an approximate like the gradient, right? It'll kind of be, we're hoping this is a sort of representative sample, and therefore the direction it points for the gradient is going to be sort of representative of the entire population, okay? And so we get like we get the gradient based on this 10, which we hope is at least in a similar direction as the gradient of the entire thing. And then we just do this again and again and again. So every single time I'm going to just randomly sample 10 different values. We use that to get a gradient, and then and that should point, hopefully mostly downhill. And so we do gradient descent that way. Okay. And so gradient descent, we're going to use the same code that we had on Monday, which basically will say, all right, given, in our case, the batch that we have, the 10 images that we have, do forward feed to get your y-hats. Once you get your y-hats, calculate your gradients. And this was based on the work that we did, I guess, on Friday and Monday, where we calculated the gradients. And then once you calculate your gradients, you just take your current value of your weight matrix and you subtract off a scalar times the gradient, right? And then we just repeat over and over and over again. So I will go ahead and do this. Okay, and so everything here, so this is the training, and I guess what I'm trying to show you is that we're not doing anything magical here. Okay, we're just doing matrix operations. We went through the work of calculating these gradients ourselves and whatnot. Okay, and this, in fact, this trains a neural network, and we're going to get decent performance with this. So let's. We have our network. It went through all 60,000 images. It did gradient descent, 10 images at a time, and basically used that to figure out the gradient and walked downhill. And so now we have a matrix W1 with some values. These are our trained weights, and this is the output. Okay, this is when they talk about like large language models like ChatGPT, and they have like these basically. It's a big neural network with billions of nodes, and they've spent like billions of dollars running computers to just get the proper weights. And nobody has any idea what these weights are, but these are the magical weights that now, like when you put the input in, it creates the output, okay? And so those weights are the secret values that make the network do it. Nobody knows what any of them mean, but those are like, there's like a whole thing of like, we have to protect these weights because these are this is what makes the network valuable, right? This is what gives us the performance. But anyway, we have the weights now, okay? And you know, ours took a few seconds because it's a small network and it's a simple training data set. But anyway, let's test this out. Okay, so I'm going to do forward feed with our test data. Okay, so xt represents my test data, and I'm going to take my test images. I've got 10,000 test images, and I'm going to just forward feed them through the network now that I have trained weights on W1 and W2. So that's all I'm doing right now, is I've taken all of my trained weights in W1 and W2, and I'm doing forward feed. So my test data, we multiply by W1, apply the sigmoid function, take that, multiply by W2, apply the sigmoid function, and then and basically the output of y hat. So remember, our target values are all, like, you know, all the nodes are zeros and one node has a 1, okay? When I look at my y hats, okay, let's, I guess let's do just head. Okay, ooh, hard to read. Here, let me round it. Round to, let's say, 4 decimal places, okay? This is what our output looks like, okay? So the targets should be all like, so our first image is, okay, this is our first image, and we can see it's 0.002, 0.000, 0.0024, you know, so we're getting, remember the target was probably all zeros, and then here we have something close to 1, 0.9998, and then here, these are pretty much 0, like, well, this is 0, and this is 10 to the minus 4, okay, so a really small value. So this would correspond to a digit. We have a 1 in this node, which would be the node for label 7, okay? 7, 8, 9. All right, so we would expect this first image to be a label 7. The second image, we have a 0.8863, so not quite, you know, what we want to see is like 0.999. We didn't get 0.999, we got 0.8863, so it says, you know, but we're pretty confident it's a 2. Okay, we have a 0.05 for a label 3, and then pretty much zeros everywhere else. Now, one thing to note is that these are not probabilities, okay? There's no requirement that each row has to add up to 1 or anything like that, okay? We're just saying, you know, when we said your mistake is basically how far you are away from all zeros and a 1 or something like that. And so it's just trying to get that. So you can see, you know, like if I add up this row, it doesn't add up to 1. We get something greater than 1. So the rows aren't probabilities. We're hoping for a bunch of zeros, okay? And we see something very close to a bunch of zeros, and then something close to a 1. So that would correspond to a label 1. This corresponds to a label 0. This one would correspond to a label 4, okay? And, you know, let's see how it is. So basically, I just said for the guess, just tell me which column has the maximum value, and it's going to give me either like columns 1 through 10, and then we'll subtract off 1 to get the label. So my first guess is a 7, and then let's take a look at that image, and what we're hoping for is something that looks like the number 7, and indeed, it labeled it correctly, okay? Our second one, we're guessing, is a label 2, and that's based on, you know, 0, 0, and 0.8863. And let's see what that image is. Yep, that looks like a number 2. Okay, our third image is a 1 that's, you know, 0.9996. That should be easy, right? Yep, that's a number 1. Our fourth one is a 0, and that looks good. Okay, so, you know, ta-da! Okay, so our neural network has taken our training data, and again, the training process is just figuring out what weights to go into, you know, our first and second weight matrix, or our W1 and our W2, and we just did gradient descent using these matrix operations and subtracting, and it seems like it's working. Okay, so we can test. We can go ahead and figure out what all of the labels are, and I'm going to table these results and compare them to their actual values, okay? So here I have the actual labels. The actual labels are 0 through 9, and then I compare them to my guesses. And the diagonal is things that we've labeled correctly, and our off diagonals are things that we labeled incorrectly. So when it was actually a 0, we guessed 0 941 times, but we sometimes guessed the number 2, sometimes we guessed the number 3, sometimes we guessed the number 6, and that kind of makes sense, right? 0 and 6 are probably, sometimes we guessed a 4 and sometimes we guessed an 8, okay? When the actual number was a 1, we guessed number 1 1,113 times, and we guessed these other things, this and stuff like that, right? So the off diagonals, so it looks like we often get 3 and 7 mixed up. I don't know. We also get 5 and 6 messed up. Oh, a common mistake is a 9 and a 7. Okay, and that kind of makes sense, I guess, right? But anyway, so let's just kind of see what some of our mistakes are. And I just say, hey, where did you not get it correct? Okay, so we mislabeled image number 9, and I'm just curious what my output matrix is. My y hat for row 9. Let's round that. Okay, 1, 2, 3, 4, 5, 6. So we labeled it, what did we label it? We labeled it as 6 or something. Okay. Oops. The actual value was a 5, and we labeled it as, our guess was a 6. Okay. And we say, well, I'm not too upset about this. Okay. Our neural network guessed a 6. And the actual label was a 5, okay? And we know the reason why we know the actual labels is because it says like this is going to Cincinnati, and we know the actual zip code for Cincinnati. So we like, even if it's like hard to read, we can say like, okay, they meant to write the number 5 there and stuff. Okay, so anyway, I don't know. This is a mistake that the neural network made, but we're also like not too angry about it either, okay? Here's another image that it messed up. Okay, so the actual label was a 5. Let's see what our y hat thought it was. Okay, so it wasn't super confident, but it guessed 1, 2, 3. It's guessing a 3, 4, 5, and it's kind of undecided between a 3 and a 5. Okay. So it guessed a 3. The actual label is a 5, and yeah, we say, okay, yeah, that definitely looks like a 5. Our neural network labeled it a 3, but it wasn't like super confident in the label of 3, right? The label it gave 3 was 0.71, and it gave the 5 a 0.268. So, kind of, it got it wrong. It got it wrong, but it wasn't like completely super far off base. Okay, and we can kind of go through and investigate some of these other entries. I don't know. These are all mistakes here, and so I don't know. 4808. Let's just take a look at that one. So here is the actual label is an 8. Our network guessed a 3, and yeah, I mean that's definitely an 8. I am curious what the y hat is. What that thing is. So it's not anywhere close. It guessed either it was between 0 and 3, and the 3 wasn't very confident. It was 0.5729. Okay, but that's an 8. But anyway, this is our neural network kind of performing as far as labeling digits, and that's what we have. This is the MNIST data set, 28 by 28 pixel images of handwritten digits, and we just have a simple neural network, 30 nodes in our hidden layer. But yeah, all of the big bigger networks that power so many things today, like the automatic image recognition. You go on Google and you search images and it finds all of this stuff. And then, on your phone, you can say, hey, show me all of the pictures I took of cats, all right? And it's able to go through your pictures and recognize all of these things, even though you never labeled and said, like, this is a picture of a cat. It has figured it out. And it's all based on neural networks. It's certainly much bigger networks, more complicated ones. We have layers, and the connections aren't going to be like all of the nodes here are connected to all of the other nodes. We have like dropout, we have convolutions, we have these other things. The large language models use a certain design called attention, where they're keeping track of something else. But at its core, it's just a bunch of matrices being multiplied together. Or I guess you have these higher dimensional structures, so like larger arrays, not just two-dimensional matrices, but like 3 or 4 dimensional arrays, which we call tensors. But they're just all being multiplied. You have this back propagation. Your gradient descent is still the primary algorithm used for training. Maybe some modifications of it. But yeah, that's what's happening under the hood. And anyway, I think it's kind of neat. And that's it. Let me give you your last 2 view quiz answers. Second answer is D as in dog. And third answer is A as in apple. Okay? And you can play around with this. The code that I've posted on Brew and Learn should work. Again, just follow the instructions for downloading it. Make sure you have your subfolders set up correctly, and you unzip or unzip your data, and it should work. All right. Have a great weekend. Some of you I'll see at DataFest, and otherwise we'll see you Monday.